Okay, welcome back everybody. This section is called summation. And ideally you see this word sum right inside of everything. This is just a very fancy way of summing objects, but it relates directly to sequences because of the following. So a summation is the process of summing over all elements in an indexed set, aka sequence. So if you start with a sequence, what you can do with the summation is you can sum over everything in the sequence. So a really natural example would just be the following. Let's look at a sub n equals 1 to 3, with a sub n equals n squared plus n plus 1. Then, I can make this explicit by rewriting it as n squared plus n plus 1, going from 1 to 3. And if I evaluate that on each of the 3 entries, that's 1 squared plus 1 plus 1, so 3 is my first entry, then 2 squared plus 2 plus 1 is 7, and 3 squared plus 3 plus 1 is 13. A summation, okay, so a summation of this indexed set is given by 3 plus 7 plus 13. And you just go ahead and add those together, you get 23. So there's nothing more complicated to summations than what I just showed you, except that it's got its own notation associated to it, and sometimes there are infinitely many entries. So I'll say the complicated parts of summations are, well, first, notation. And there are 2 of these that we'll cover. We'll cover something called sigma. It's a Greek letter, and it looks like this. So you all get good at drawing that Greek letter. And that's the capital sigma, by the way. There's a lowercase sigma as well. So there's sigma notation. And there's also Einstein. Yes, named after Albert Einstein notation, which is going to look something like this, where it looks like I have 2 index sets that use the same number. So Einstein, I've got 2 index is with the same variable. In sigma, we have the Greek letter. And you've probably seen in all sorts of TV shows, etc., when people like to be mathy, they'll use that sigma notation. Very common notation. The second complicated part is that over infinite sets, we must define an infinite sum. Whatever that means, right? So you have to define what an infinite sum would mean if you start with an infinite set. So those are really the complicated parts. Let's go ahead and tackle our notation first. Let's get notation over with. Okay, so as far as sigma notation exists, it's not too bad. It's not too bad. So all I need to do is if I have a sequence, here it is, a sub n, and then let's just make n in an arbitrary index set for now. I mean, I could definitely put a natural number there if I wanted to. I could use n or z, etc. But let's just stick with I for now. If I have a sequence, then the notation sigma, and then you write n in I, the index set, underneath. Okay, so that goes underneath the sigma. And then you don't write the brackets. So we're not going to write the brackets in sigma. What we're going to do is just write a sub n. No brackets. So that notation describes the summation a of n1, an2, an3. Okay, these are all added together, right? And so on. So it just describes the sum of all of those. And maybe that sum terminates, maybe it doesn't. So let's look at an example. We could use our earlier example if we want to. Let's switch it up a little bit. Let's do c sub n. N is in the index set 1, 3, 5, and 7, where Cn equals n squared minus 2n. Okay, so what does this mean? Compute sum n in 1, 3, 5, 7 of Cn Well, I know what Cn equals. Cn equals n squared minus 2n. And so then this summation is just me. I'm just going to take a sum over each entry in the indexed set. So I'm just going to grab this 1, I'm going to plug it in. What does that give me? It gives me 1 squared minus 2 times 1. I then add the 3 plus the 3, which would be 3 squared minus 2 times 3. I then add the 5, which is 5 squared minus 2 times 5. Then I go ahead and add the 7 as well, plus 7 squared minus 2 times 7. So what do I end up with when I add all these terms together? It looks like 1 squared minus 2 is negative 1, plus 3 squared minus 6 is going to be 3, 5 squared minus 10 is 15, and 7 squared minus 14 is 35. If I just add all those together, it looks like 53 minus 1 is 52. So that is the sum. So it's not too terribly complicated, even using the sigma notation. And of course, we'll encounter more of these in the worked examples section. But what may be complicated is the following. Let's look at the following. One more example. And we'll get into kind of these infinite cases even more later, but let's look at this example. Let's do 1 divided by n squared, where n is in the natural numbers. Consider the sigma notation, n in the natural numbers, 1 divided by n squared. And just like with sequences, I can play this lower and upper bound game. Let's say lower bound and an upper bound. And of course, since I use the natural numbers, that's why my upper bound is an infinite. 1 over n squared. If I write this out just as I wrote out the kind of the previous sum, just plugging each term in and adding them together, well, that's going to be plugging in a 1. I get 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus so on. Okay, so that's 1 plus a quarter plus a ninth, and so on. It's not really easy to tell what this should be equal to. And in fact, even in this course, we can't get into too much how you would calculate values like this. This is actually a very difficult math problem to calculate in closed form, but it's important to recognize that these sorts of things exist and you can actually compute their limits. The limit here is going to be pi squared over 6. And actually, it turns out it was Leonhard Euler, the same guy who has that number E named after him. Leonhard Euler proved this, and he got pretty famous for doing it. So, don't try to do these too often, but it's important to recognize that even over infinite sets, these do have some well-defined notions, because what would you notice here is that you would notice the sum get close to the limiting answer. It's just like any other sort of limits that you would work with. So that's another example using that sigma notation. And now we're going to switch over to this Einstein notation. So the Einstein notation is actually more useful and used in physics. Say Einstein notation. I'll say it's incredibly common in modern physics. Okay, so by modern physics, I mean anything from general relativity to quantum field theory to particle physics. Okay, probably those three. So Einstein notation is probably what you'll see if you decide you want to head into any of those directions. And even if you don't, you'll periodically encounter it. And it's a very useful notation. Okay, so how does this work? So a summation, and I'll say subject to Einstein notation, is defined by placing two sequences of the same index set. So not only does the index set have to be the same, and same index variable. So you have to use the same set and the same variable, and you place them next to each other using one superscript and one subscript. So as an example here, which I already kind of showed, but let's do it in reality. Let's do Cn from 1 to 4 with Cn is defined by n plus 1, and let's do d sub n goes from 1 to 4, with d sub n is defined by n squared minus 2. An Einstein summation occurs when we place C with a subscript n next to D with a superscript n. And is interpreted as the sigma notation, sigma C n d n n equals 1 to 4. And so there is an implicit multiplication. So there's a multiplication which occurs in Einstein notation that doesn't necessarily need to occur in regular sigma notation, right? When I jump up here, I wasn't multiplying two sequences together. When I write down my sigma notation, I'm able to write the sigma notation of a single sequence. It's just the summation of Cn. You can't play the same game with Einstein. Einstein you're stuck starting with two sequences and combining them together. Okay, and so what would this look like? This would look like C1 D1 plus C2 D2 plus C3 D3 plus C4 D4. And we could write out what each of those is actually equal to based off of its definition. C1 would be placing a 1 there, so that would be 1 plus 1. C1 would be 2. D1 would be placing a 1 there. 1 squared minus 2 is negative 1. C2 would be placing a 2 there, so you'll have a 3 times a 2 there will be a 2 plus 4 times placing a 3 there would be 7 plus 4 there would give you a 5, and a 4 here would give you a 14. So if you actually multiply these out, you get negative 2 plus 6 plus 28. 5 times 14 is 70, I believe, plus 70. What do we have? We have 98 plus 6 is 104, minus 2 is 102. And so Einstein summation would give you 102 if you go ahead and just write. You would literally write out that Cn dn, by the way, still no brackets. Still no brackets needed for Einstein. And you would just put them next to each other as long as you have the alternating subscript and superscript, and then you would know to add them all together over their index set. So that's the Einstein summation notation, as people will say. And let's go ahead. We can play a quick game with one more example with Einstein, jumping up to kind of this one that we saw before with this 1 over n squared game. Let's see the Einstein summation version of that. If we did something like, let's say x sub k is 1 over k, and y sub j is 1 over j, then by Einstein, we can write, okay, technically these need index sets, so we would say k is in n and j is in n. But once the index sets are the same, by Einstein, we can write something like x sub p y to the power p. Once again, notice that I made sure that that was the same letter, and in fact I moved the j up top. Move for Einstein, you have to move it up top, but once you move it up top, you say, oh, look at that, there's a subscript and a superscript, so this has to be x1 y1 plus x2 y2 plus x3 y3, and so on. And if you actually write this out, you get 1 divided by 1 times 1 divided by 1 plus 1 divided by 2 times 1 divided by 2 plus 1 divided by 3 times by 3 plus dot dot dot. Or you still have this beautiful Euler identity that this will be pi squared over 6. And so Einstein also works for these infinite sums as long as you're starting with infinite indices. I'll write an example where Einstein does not work. So if I wrote x p y p, this is not Einstein. So no summation, because not superscript subscript. If I write x sub p y to the q, also not Einstein. So no summation, because names of variables are different. So you're really looking for both the subscript and superscript to agree for Einstein to apply. Let's finish off with infinite sums. I realize I technically introduced them, but I didn't describe kind of how we actually compute them. So how does one handle summations over infinite sets? Well, the fun thing is you can construct a sequence of partial sums. So this thing is truly a sequence of partial sums of sequences. This is like the meta version of sequences, right? Not Mark Zuckerberg meta, like meta philosophical meta. So we can construct a sequence of partial sums themselves of sequences, okay? So how do we do this? Well, we could say something like, consider the sequence a sub n, indexed maybe by the natural numbers. This gives rise to a new sequence, S sub n, S for sum, also in the natural numbers, defined by Sn equals the sum, and here I'm using the sigma notation, n starts at 1, but it ends at, and actually I'll say m starts at 1 and it ends at n. Okay, so we're looking, that number, or that variable and that variable are the same. Same variable. Over here, this is the variable associated to am now. And so what we can do is we have this sequence S sub n, whose elements are defined by this entire structure. And now we can ask if the sequence Sn has a limit. You know, do its values get closer and closer to a true value? So let's look at one example of this, and we'll finish up. So our one example of this will be like, does this sum, let's do k over k cubed plus 1, k starting at 1 and going to infinity, exist? We need to check, well, we first need to construct the sequence Sn defined by Sn is the sum where I'm placing the n up top here, right? So n and n, these are the two that compare to each other, and I can place a k inside of here, k cubed plus 1, then compute each entry of this sum, or this sequence, and check if there is a limit. So what would that mean? That would mean, let's look at the S1 case. Well, S1 is this sum, k equals 1 to 1, k over k cubed plus 1. So I'm going to do every entry in here starting at 1 and ending at 1. Well, that's not too bad. That's exactly this entry, also known as 1/2, or 0.5, because pretty soon it's going to be to my advantage to use decimals. S2 will be the case k equals 1 to 2. So here I'm going to have 1 over 1 cubed plus 1 plus 2 over 2 cubed plus 1. This will give me 1/2 plus 2/9, or in decimal, 0.72 repeating. You can look at S3. This is going to be the sum k equals 1 to 3, k over k cubed plus 1, which will be 1 over 1 cubed plus 1 plus 2 over 2 cubed plus 1 plus 3 over 3 cubed plus 1, also known as 1/2 plus 2/9 plus 3 over 28, which in decimal is 0.8294. And then let's skip quite a few, and maybe let's jump up to S500, which would be the sum k going from 1 to 500, k divided by k cubed plus 1, which is 1 divided by 1 cubed plus 1, plus 2 divided by 2 cubed plus 1 plus dot 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 plus the last two terms, 499 over 499 cubed plus 1, and then 500 over 500 cubed plus 1, which in decimal is 1.1018. And believe it or not, if I tried S501, a lot of dots there, but I would get 1.1018. And so what you see is that, by the way, it's not changing as I move from 500 to 501. That means that the limit exists. And this sum, the one I was originally interested in, out to infinity, k divided by k cubed plus 1 is 1.1018, and it would just continue after that point. But it would have a non-infinite limit, which is kind of cool to see. Now, it turns out, because you have sequences, because there are such things as sequences of functions, right? I just want to comment on this before we finish as a remark. Because there are sequences of functions, one may consider summations and limits of summations of functions. This is pretty cool. So we're going to start to see a couple of these. It'll take us maybe a week or so to see something like this. It's written as Cn e to the I n x when n is in z. This is called the Fourier series. We'll see something like the summation f of n evaluated at a specific point, x minus x0 to the n divided by n factorial. We'll cover factorials later if you don't know what they are. And this is known as the Taylor series, etc. Now, this word series is another word that we often use for infinite summation. Series is a term used to mean infinite summation. So that's just kind of where we're headed, a little bit of teasing for the future. Anyway, I'll see you in the next class. Bye.